yeah, so I, as usual, want to thank the organizers for inviting me, especially because I'm not a real complex analyst. But so what I want to talk about are some things I was obsessed with actually from about 10 to 15 years ago, and then put aside because I wasn't able to prove any of these conjectures. But I hope I'll get someone here excited enough and maybe have some new ideas that it's worth going back to and trying to prove some of these conjectures. So if you want more details, I gave 4 talks about it at Queen Mary in London in 2011. So you can find those on the web. Okay, so here's the starting point. So what I call the deformed exponential function, it's just the usual exponential function series where you throw in a y to the n, choose 2. So obviously, if y is in the closed unit disk, that's an entire function of x. And it's obviously jointly analytic and jointly continuous in the usual places. So, it's been looked at a little bit, not very much, but going back to the early 20th century, it's been looked at a little bit. Valéron, in one of his articles, points out from a certain viewpoint, it's the simplest entire function after the exponential function. And it comes up in various applications. So one of them is in statistical mechanics. It's the partition function of a one-site lattice gas. So what that means is the universe consists of one point, and on that one point, you can put an arbitrary number n of indistinguishable particles. So you have some n equals 0 to infinity. The particles are indistinguishable, so that explains the 1 over n factorial. Each particle gets a weight x, and then each pair of particles interacts by an interaction y, and the interactions in a certain sense have to be repulsive so that y is of magnitude less than or equal to 1, and then that's what it is. It comes up in combinatorics as the generating function for various things on the complete graph Kn, and I'm going to show you on the next slide in a special case of that. Well, it satisfies a simple functional differential equation, namely differentiating with respect to x is the same as multiplying x by y. So it has been studied by people who study functional differential equations or delay differential equations. And it comes up in complex analysis with the Whittaker and Goncharov constants. I forget exactly what they are, but they're various inequalities for entire functions. And I think it's believed that the worst cases for those inequalities are special cases of the deformed exponential function. Okay, so let me show you an application to the enumeration of connected graphs. So let's consider all connected graphs on n labeled vertices. So we have vertices labeled 1 through n, and we consider all possible connected graphs with a weight v for each edge. And then you form the generating polynomial for those things, right? So the smallest ones are the trees. You have n minus 1 edges, and there are n to the n n to the n minus 2 of those. And then there are various others. So you have this generating polynomial, and no explicit formula for it is known. But we can find the exponential generating function of these things. And the way to do it is, let's ask the same question, not for connected graphs, but for all graphs. And then the answer is easy. With n vertices, you have n choose 2 possible edges, and each possible edge is either empty with weight 1 or present with weight v. So you simply get 1 plus v to the n choose 2. So that's obvious. And then in enumerative combinatorics, you have something called the exponential formula, which basically says if you have stuff on labeled vertices, and stuff is a disjoint union of connected stuff, then the exponential generating function of the connected stuff is the logarithm of the exponential generating function of all stuff. So that, and then the exponential generating function of all stuff you see is the deformed exponential function evaluated at y equals 1 plus v. So that's one way where this deformed exponential function comes up in a very interesting combinatorial application. Usually combinatorialists will consider this as a formal power series in X, especially because they're often thinking in the back of their mind that V is positive, right? You give positive weights to edges, and then the series really would be divergent. But if you're in the disk 1 plus V less than or equal to 1, then the series are convergent. So you can consider this also from an analytic point of view, and I will. Okay, so let's go back to the pure analysis. Let's just talk about some elementary analytic properties of this function. Well, one of the important ones for this talk will be when y equals 0, the function is 1 plus x. That will play an important role. The most interesting thing is when y is in the open unit disk and not y equals 0, this is a non-polynomial entire function of order 0. So it has a Hadamard factorization in terms of its zeros. It basically is something like a polynomial of infinite degree, right? It factors like a polynomial, but of infinite degree. When y equals 1, it's just the exponential function. And when y is on the unit circle, not at y equals 1, it's an entire function of order 1 and type 1. So it has a Hadamard factorization with 1 subtraction. So that goes back to Alander when y is a root of unity, and then various other people, including Alex, when y is on the unit circle, not a root of unity. And finally, when y is outside the unit disk, the series has 0 radius of convergence, so it makes no sense. Okay. So what consequences does this imply already for the generating function of connected graphs? Well, let's make this change of variables y equals 1 plus v. Then for y in the open unit disk, we have, is there a pointer here? Which is
the first button.
No, the first button.
Top button.
Good. The top button moves things. No.
Very common.
This one.
No, I'm going to go back. Wait, sorry, which button? No, the top one. Oh, I see. It's also a pointer. Ah, okay. Good. Thank you. Okay. So, oops. Right. So when y is in the unit disk, we have this exponential generating function is log of the deformed exponential function. We put in its Hadamard factorization in terms of the zeros, and therefore we get an explicit formula for the generating function of connected graphs in terms of the zeros of the deformed exponential function. And I stress, this is a convergent series. So this is a little bit bizarre. These x, k of y, those are the roots of the deformed exponential function. We don't know how they depend on y. They may be analytic, but they may not be. There might be collisions of roots and branch points. So who knows what the x, k of y are? But whatever they are, they sum up to this is a polynomial in y of degree n choose 2. So this is an amazing formula. In particular, it gives an asymptotic expansion if the deformed exponential function has a unique root of minimum modulus, then this will be dominated for large n by the unique root of minimum modulus, and everything else will be exponentially small. Okay, so you can see that these zeros of the deformed exponential function are very important for understanding the behavior of this generating the graphs. And so we wanted to know, what can we say about these roots? Okay, so the first thing I want to talk about is the small y expansion. So when y equals 0, the function is 1 plus x. So it has a 0 at minus 1. So when y is small, you expect a perturbation expansion around the 0 at minus 1. You expect a power series like that. And it's easy to show using Roche that this is indeed the case, that in y, a disk of that size, there is a unique 0 that's given by that convergent expansion. Okay, good. And more generally, for each integer k, what you can do is scale x as y to the minus k. Then, and put it in, then what happens is that shifts the y to the n choose 2 gets shifted to y to the n minus k choose 2. And then that series is dominated for small y by the terms n equals k and n equals k plus 1. And therefore, the kth root also has a series. The k plus 1 comes from the ratio of the factorials. You have the y to the minus k, and then you have a series in y. And you can make this Rouchet argument valid uniformly in K in a slightly smaller disk. So in the smaller disk, you're guaranteed that all the roots are simple and they're given by the convergent expansions xk of y. Okay. And Alex Eremenko pointed out to me many years ago that you can also use the theta function in the Rouchet argument and get somewhat better bounds. Okay, so then I ask, these series, we know they converge in some small disk in Y. Might they converge in the entire unit disk? Well, there are two ways that this zero could fail to be analytic. One is you have a collision of roots, and then you'll get a branch point. Second possibility is a root could escape to infinity, and you get maybe a pole. Okay, so Alex proved a theorem in 2009 in an email to me, and it's never been published, but I can dig it up, that says no root can escape to infinity for y in the open unit disk. And more precisely, the theorem is for any compact subset of y's, a compact subset of the unit disk, there's an integer k0 where basically all the zeros beyond k0 are well controlled by these series. You have a simple zero that's within a factor 1 plus epsilon of where the series says they should be, and there are no other zeros. And inside this, inside a certain disk, you know that there are exactly k0 zeros. You don't know where they are, but they're there. So it's a Rouchet argument also. So basically, you control very well the zeros outside a certain disk, and inside the disk, you control how many zeros there are. And so the proof is based on a comparison with a theta function, because for the theta function, you know where the roots are by virtue of Jacobi's product formula. And this series looks vaguely like a theta function.
Can I ask a quick
Yeah,
question?
oh yeah, please do interrupt, yeah.
Because you mentioned theta functions. So is there a relation of your modified exponential functions with modular forms?
I don't know. I would guess not, but I don't know. I mean, I know nothing about modular forms, but I would guess not. You'll see something that's a little bit closer when I discuss the partial theta function, which is the same series without the 1 over n factorial. That might be a little bit closer, but probably still not close enough. But those are all interesting questions.
But also the theta function has a lattice parameter, right? How does the
Yeah.
lattice parameter depend on your?
You mean the Q? The Q is the
Okay,
Y.
fine.
Q is the
Q
Y.
is
Q is the, yeah. In fact, I should say my Y, many people would prefer to call it Q.
Okay.
Okay, and by the way, I conjecture that the roots don't escape to infinity even in the closed unit disk, except of course at y equals 1, where the roots do escape to infinity, because the exponential function has no zeros. So as y approaches 1, the zeros have to go to infinity. But aside from that, I conjecture that Alex's result can be generalized to the closed unit disk, but I don't know how. Okay, so now let me make some conjectures. I'm going to make a lot of conjectures. I'm going to make a big tower of conjectures where you'll see some of them imply others, and I don't know how to prove any of them. Okay, so big conjecture number 1. So Alex has ruled out that a root could escape to infinity in the open unit disk. I conjecture that there are no collisions either. So I conjecture that all the roots are simple. And since there are no collisions, it follows that each root is analytic in the open unit disk. Okay, that's the first big conjecture. But I conjecture more than that. I conjecture that not only do the roots not collide, they're non-crossing in modulus. At small y, we know that's the case. At small y, x0 is of order y to the 0, x1 is of order y to the -1, or to the y to the -2. They're very far apart at small y. I conjecture that they stay ordered like that in modulus. And if they stay ordered in modulus, then it's an easy consequence that they actually stay separated in modulus by a factor at least absolute y. That just comes from applying the Schwartz lemma to the ratio. So those are my first two conjectures. Now let's look at the consequences for the zeros of this generating polynomial. So the generating polynomial is given by a sum like that. So it's a little bit like, it's kind of like trace of a matrix where xk of y to the -1 are the eigenvalues. And this is something like trace of matrix to the n. And there's a theorem, whenever you have a situation like this, there's a beautiful theorem due to Baraha, Kahan, and Weiss that goes back to, I think, 1979, which basically says, if you ask, where do the zeros of Cn of y accumulate as n goes to infinity? The answer is they accumulate at the places where there is not a unique eigenvalue, well, in this case, a unique xk of smallest modulus. You have two of these eigenvalues of smallest modulus competing, and the competing makes phase oscillations that cause zeros of the Cn of y. That's basically what the Baraha-Kahan-Weiss theorem says. And so the limit points of zeros are the places where the zero of minimum modulus is non-unique. And so if, as remember my big conjecture 2 says that the zeros stay separated in modulus, in particular, that implies that x0 is the unique zero of smallest modulus. And then it would follow that the zeros of these generating polynomials do not accumulate anywhere in the open unit disk. Okay, so that would be a consequence of a very, very special case of big conjecture 2. But I actually conjecture more. I computed the zeros of these things up to about n equals 80. And it seems they don't have any zeros in the unit disk period. Not just don't accumulate, there are no zeros in the unit disk for these polynomials. In fact, I suspect no zeros on the unit circle except at the point y equals 1 where they do have zeros. Okay. What's the evidence for these conjectures? Well, the first piece of evidence is the behavior at real y. If y is between 0 and 1, then there's an old theorem of Laguerre that says all the roots are simple and negative real. Okay. And so in particular, each root is analytic in a complex neighborhood of the interval 0, 1. But we have no idea how big that neighborhood is. Now, combine this with evidence from the numerical computation of these series. So just quickly, there are various methods for computing these series. One is you just plug in the ansatz and solve term by term. Another is you use something that I call the explicit implicit function theorem. So it's a generalization of the Lagrange inversion formula that I worked on about 15 years ago. You can use that. And each of these methods will get you more terms more efficiently. And these two methods also work symbolically in K. That is to say, you can compute all of the zeros at once with coefficients that are rational functions of K. Third method is to plug in this ansatz together with a known recurrence for the generating polynomial of connected graphs. And using this method, I got the leading root to about 900 terms. But an even better method is to use this iteration that was invented by various people in the 19th century for finding zeros of polynomials numerically, which is basically just a repeated squaring method. And you can use it at the level of formal power series. And so I got 65,535 terms. I don't think you want to see that file. Each coefficient is 100 megabytes. Anyway, so here is, for example, here's the leading root. So 1 plus 1/2 y, you see the roots of various rational numbers. The coefficients in this series are various rational numbers. What do you notice about these rational numbers? I can't make any head or tail of what they are, but all these terms are non-negative. Strictly positive, and I've verified that through 65,000 terms. Okay, So this is the first surprise. I mean, I first saw this up to 20 terms and then gradually, saw more and more. So this is amazing, right? The coefficients of the leading root seem to be all non-negative. And so, and the same thing seems to be true for the higher roots also. So that's my big conjecture number 4. All these series have non-negative coefficients. Well, if that's true, the Vivanti-Pringsheim theorem says that if you have a power series with non-negative coefficients, the leading singularity is on the positive real axis. But if we have analyticity on the interval 0, 1, it means there are no singularities anywhere in the unit disk. And so we get, as a consequence of this big conjecture 4, each root is analytic in the open unit disk. So that's an amazing fact if it's true. There will be no collisions. And so I need to do further computations, but I think the evidence already suggests that it's very likely true. Okay, but more turns out to be true. Let's look not at the 0, but the reciprocal of the 0, which is the thing that comes in the Hadamard formula. What do you see? 1 minus stuff, everything negative through order 65,000. Okay, now this becomes even more interesting. So first of all, I conjecture that's true for all the series, not just the leading root. And it implies the previous conjecture, but stronger, right? If you have a series 1 minus blah, its reciprocal is 1 plus blah, but not inversely. One thing, the coefficients look a little bit simpler than in X naught. So maybe they have a simpler combinatorial interpretation, if there is one. But maybe more interesting. It's easy to see as y goes to 1, I think I mentioned it, as y goes to 1, the exponential function has no 0. So as y goes to 1, all the zeros have to go off to infinity, in this case to minus infinity. And so therefore the reciprocal has to go to 0. Now you take 1 minus blah, and when y goes to 1, blah has to add up to 1. So all of those coefficients, where you take away the minus sign, positive numbers that add up to 1. Now, what do you call positive numbers that add up to 1? I don't know about you. I call it a probability distribution, right? So those coefficients are the probabilities for a positive integer valued random variable. What on earth is this random variable? I don't know. Okay, but I conjecture once again that even more is true. Remember, so first of all, so remember we have this generating polynomial of connected graphs. I will divide it by this -1 to the n minus 1, n minus 1 factorial, so that the constant term is 1. And recall that you got the leading root just by taking this polynomial to the power -1 over n and taking the limit. So these polynomials dn of y are kind of generalizations of this leading root x naught of y. It's a whole sequence of stuff that might have properties analogous to what the limit has. And that's what I conjecture is true. I conjecture that dn of y to the -1 over n has all non-negative coefficients, or even more strongly, dn of y to the +1 over n has all non-positive coefficients after the constant term 1. And once again, the big conjecture 6a implies by Vivanti-Pringsheim what I conjectured earlier, that this generating polynomial has no zeros in the unit disk. So that thing which seemed like a surprise earlier, now you can see it's a consequence of this deeper conjecture. And secondly, big conjecture minus 6b shows that the coefficients in this series are, again, the probabilities for a positive integer valued random variable. So now we have an infinite sequence of positive integer random variables indexed by n that approach the one I mentioned on the previous slide. So this would generalize the one for 1 over x naught in roughly the same way that the binomial generalizes the Poisson, right? And what might such a random variable be? Well, we have this probability generating function for each n. Presumably it has something to do with random graphs on n vertices, but I don't know what. I mean, even for n equals 2, I don't know what. It maybe is some kind of structure built on top of a random graph, some kind of tree or Markov chain or who knows what. I'll try to understand the first two cases. I mean, P2 of y, it's obvious from the binomial expansion that those are non-negative. And I mean, it's a known random variable, but I was unable to make any sense of, what this really means. For P3 of y, I have, well, for P3 of y, I have an analytic proof. It's not totally trivial to see that all these coefficients are non-negative, but I do have an analytic proof that these coefficients are non-negative, but it doesn't shed any light on the possible probabilistic interpretation. And Jim Phil has a probabilistic interpretation for n equals 2 and n equals 3 in terms of birth and death chains. That is to say, random walks on the non-negative integers. But it doesn't seem to generalize to n greater than or equal to 4. So, okay, so let's now go back to this issue of the separation in modulus of the roots. You can look at the series for the ratios. The series for the first ratio, x0 over x1, seems to have non-negative coefficients. And so that's another big conjecture. And a consequence of that is, since as y goes to 1, that ratio approaches 1, it must be that x0 is less than x1 in the unit disk. And so that would be a special case of this big conjecture number 2 on the separation in modulus of the roots. Okay. Unfortunately, if you try to do this to the next ones, like x1 over x2, the coefficients are not anymore non-negative. That doesn't contradict the conjecture that it's bounded by 1 in the unit disk, but it does rule out the simplest proof. So one thing I would need to do is to try to compute the Schur coefficients of these series to see whether they do indeed represent analytic functions that are bounded by 1 in the unit disk. So there are various computations that need to be done that I didn't have time to do. One other thing you can ask about is the asymptotics of the roots as y goes to 1. That's very interesting. So you want y goes to 1, so it makes sense to write y as e to the minus gamma and ask gamma going to 0 non-tangentially in the right half plane. So equivalently, y going to 1 non-tangentially in the unit disk. And I think the story is the following. So we know that the zeros have to go off to infinity. I believe they all go infinity together. It's funny, at small y, they're all going with different inverse powers of y. But as y goes to 1, I think they all go together as 1 over y with the same constant 1 over e, and then different subleading corrections. But I haven't yet worked out all the details. The method is basically you develop an asymptotic expansion in the regime where y is going to 0 and x is of order y to the minus 1. So you'll write x is y to the minus 1 times something. And then there will be 3 regimes depending on whether something is less than 1 over e, greater than 1 over e, or near 1 over e. You do a saddle point method. And once you get an asymptotic expansion for the deformed exponential function, you use it to get an asymptotic expansion for the zeros. And anyone who's knowledgeable about Airy asymptotics who would like to collaborate, happy to go back to this. I mean, I can dig up my notes from 15 years ago. I mean, in other words, I believe I understand formally how this expansion works. And the problem is, how do you deform the contour in order to guarantee that the integration is really dominated by the saddle point? Okay. But now let me switch gears a little bit. Well, I want to look again at this leading root x0 of y as a power series in y, but in a somewhat more general context. Then I consider a formal power series with any coefficients alpha n you like, x to the n, y to the n, choose 2. Okay, They could be 1 over n factorial, but they don't have to be. I'll normalize them to alpha naught, and alpha 1 is 1. And so one example is this partial theta function. It's like the deformed exponential function, but with 1s rather than 1 over n factorial. So Q series people have looked at this quite a lot. It's not as nicely behaved as, so it's called the partial theta function because the ordinary theta function is basically the same sum, but we run it down to minus infinity. And it doesn't have all the nice properties that the ordinary theta function has, but it has some nice properties. And more generally, you can look at this Rogers-Ramanujan entire function where you have x to the n, y to the n, choose 2, and then you have these are so-called q factorials in the denominator. And the point is, at q equals 0, this is the partial theta function. At q equals 1, this is the deformed exponential function. So this is a q interpolation between the deformed exponential function and the partial theta function. And then I'll show you some even simpler interpolations, what I call the deformed binomial and deformed hypergeometric series a few slides down. Okay, so for the partial theta function, you can compute the leading root, and it's that. The series are all integers, and you can see that they're all non-negative. And there I was able to prove that the coefficients in the leading root are all positive using Q series identities. So that's the unfortunate thing. The result, as you will see, seems to be much more general than this, but the proof only works for the partial theta function because it uses various Q series identities that are satisfied by the partial theta function. So that's beautiful but frustrating. And it actually follows from these Q series identities that the stronger conjecture is true, namely the reciprocal has all non-positive coefficients after the constant term 1. And in this case, actually something even stronger is true. It's not just the reciprocal, but the reciprocal squared has all non-positive coefficients after the constant term 1, which is not true for the deformed exponential function. So as I say, alas, the method doesn't seem to generalize. It seems to be very special for the partial theta function, even though the result, as you will see, seems to be quite a bit more general. Okay, so for example, let's look at this Rogers-Ramanujan entire function. So at q equals 0, it's the partial theta. At q equals 1, it's the deformed exponential. You can prove, do you use this explicit-implicit function theorem? You can prove what is the general form of the leading root. It's a power series in Y where the coefficients are rational functions of Q and the denominator is known. The denominator is a certain product of power of these Q numbers. And the numerator is a self-inversive polynomial with integer coefficients. So that is, self-inversive means that the coefficient sequence is palindromic. So it's a self-inversive polynomial with integer coefficients. So this much you can prove. But again, empirically, I computed these polynomials Pn of Q up to, I guess, 349. Empirically, the Pn of Q have 2 interesting positivity properties. Maybe you can guess the first one. Pn of Q has all non-negative coefficients. So in particular, it will be non-negative when Q is between 0 and 1. But more than that, it's coefficient-wise non-negative in Q. So over and over again, we're getting coefficient-wise non-negativity in cases where at first we were conjecturing only point-wise non-negativity. So very strange. And secondly, it turns out to be point-wise positive, not just for Q between 0 and 1, but also for Q between -1 and 0. So I have no idea how to prove any of those properties, but I hope, I'm happy to share my Mathematica notebooks with anybody who wants to play around. Okay, here's another way of interpolating between the partial theta function and the deformed exponential function. An even simpler way, I would say. start from the Taylor series for the binomial. I'll normalize the binomial. I'll write the binomial this way: 1 minus mu x to the minus 1 over mu. The reason I write it that way is, first of all, that normalizes it so that the linear term is 1. It starts at 1 plus x. And then when x equals 1, that's just the term one, that's just the series 1 plus x squared plus x cubed, blah, 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 blah. When mu goes to 0, it becomes the exponential function. So this interpolates between the series 1 plus x squared plus x cubed and the series x to the n over n factorial. So that's what those coefficients are. And then just throw in the y to the n choose 2. So basically, you can take any formal power series you like and throw in y to the n choose 2. I'll call that the y deformation of the series. So this is the y deformation of the binomial that I've normalized in this way. And so it interpolates between the partial theta function, I'm sorry, yeah, between the deformed exponential function at mu equals 0 and the partial theta function at mu equals 1. And if you want, for mu equals minus 1 over n, it's a polynomial of degree n, which is the y deformation of the binomial. Okay. And so once again, you can use this explicit implicit function theorem to tell you what the general form of the leading root is. It's a power series in y where the denominators are explicit integers. I forget what they are, but they're explicit integers. And the numerators are polynomials of degree n in mu with integer coefficients. And can you guess what the properties of these integer coefficients are? It has all strictly positive coefficients. And once again, it's pointwise non-negative, not only for mu positive, but also for mu between minus 1 and 0. Again, I have no idea how to prove this, except at mu equals 1, where it's the partial theta function. And you can use the Q series identities to figure out what's going on. But aside from that, I have no idea how to do this. But I mean, this is just, I mean, this, all of this can't be a coincidence, right? I mean, something's going on here. And you can go further. The binomial is just the special case, the first special case of the hypergeometric series. So the exponential is the hypergeometric series 0f0. The binomial is 1f0. So you can look at the hypergeometric series pf cubed. So that means, so the hypergeometric series, when you redefine the parameters slightly the way I've done, the numerator is a product of these kind of rising powers. And the denominator is also a product of rising powers. And then you have an x to the n over n factorial. That's basically the hypergeometric function. And then I throw in the y to the n choose 2, as always. And, you know, this is a perfectly legitimate series. If you want it to be an analytic function, then, of course, there are some constraints. But if you consider it as a formal power series, P and Q can be anything. And I would also observe the way I've defined it, if you set the last mu to be 0, that just replaces P by P minus 1. And similarly for the last nu in the denominator. So in a certain sense, this is a nested family of things. As P and Q increase, they become more and more general. And you can ask what happens. And empirically, the positivity properties that I saw for the deformed binomial, that's the 1f0, seem to extend to all the pf0s in all the variables mu1 through mu_p. So this numerator polynomial ends up being a polynomial with non-negative coefficients in all those variables mu1 through mu_p. And I believe it should also be, in a certain sense, it should be possible to take p goes to infinity, because these things are nested. And so, I mean, so there should be polynomials in infinitely many variables, basically some kinds of symmetric functions that have some amazing positivity properties that I completely don't understand. I I should say the cases with non-trivial denominators are different. And I really don't know what the pattern of the behavior is. But the ones with no denominators seem to be very simple. Notice, I mean, since you're complex analysts, I mean, most complex analysts will not like to study the hypergeometric series 2F0 because it has 0 radius of convergence. Of course, once you put in the y, and y is in the unit disk, then in the open unit disk, then it does have then it's an entire function. But the upshot is, from the foremost power series point of view, P can be anything. And 2F0, 3F0, 4F0 all seem to have, you know, increasingly beautiful properties. I don't know what's going on. Okay, well, I guess I've been going too fast, but anyway, so here is a conjectured big picture. As I say, it's a conjectured big picture because almost none of this is proven. I mean, except for the result for the partial theta function, almost none of it is proven. I conjecture that there are 4 different things going on here. So first thing is positivity properties for the leading root xi naught of y. Which I'm not sure, did I introduce that notation? It's basically minus x naught of y. So either for the leading root or for the reciprocal, there seems to be positivity for a fairly large class of these general series for some fairly large class of alpha n's. It's provably true for the alpha n is 1. It's empirically true for the alpha n is 1 over n factorial, but also for the deformed binomial, for the Rogers-Ramanujan. There are lots of cases where this positivity seems empirically to be true. And so one thing you could try to do is simply find sufficient conditions on these coefficients alpha that imply, at least empirically, that these positivity properties hold. And I haven't been able to do even that. You know, I played around and tried to find some simple sufficient condition on the alpha n's that would imply empirically these positivity properties. And I don't have any good conjecture. So that's one thing you can try to do. Another thing is positivity properties for the higher roots. Well, that's more delicate. For the deformed exponential function, no, sorry, for the partial theta function, it's a blackboard. It's a blackboard, but is there chalk? Yes, there's an infinitesimal chalk.
No, this.
Oh, okay. There's some chalk here. Okay, good. For the partial theta,
You can use one of the blackboard.
and I'll use this one. For the partial theta function, so here's y, and here's negative a root, right? For the partial theta function, the leading root goes something like that, and the second root goes something like that, and they collide at some value y about 0.3 something. Okay, so the leading root does have provably have a non-negative series. The second root, I can't remember whether all the coefficients are negative, but anyway, as I recall, all of the xk for x even may have the positivity properties. So for the partial theta function, there may be some partial results about positivity for the higher roots. It may be that you have positivity of the coefficients for all the roots only for the deformed exponential. I have no idea. Third thing is you can look at positivity properties for the ratios and this whole question of non-crossing in modulus of the roots. That should hold for some unknown class of these series. I really don't know. Even for polynomials, so just take a polynomial, because so a finite power series, just take a polynomial and throw in the y to the n choose 2. Then some interesting stuff goes on. The roots move around, right? As you turn on y. In fact, again, probably the best thing is write y is e to the minus gamma. And think of gamma as time. Then the roots evolve in time according to a differential equation. And what is this differential equation? It turns out to be, after a suitable change of variables, it turns out to be the trigonometric Colodro-Moser equation. So the so-called classical Colodro-Moser equation, or more precisely, Colodro-Moser is a differential equation of second order. It's Newtonian mechanics for a system of particles with certain forces. But there is a special case of a first order equation that implies the second order Colodro-Moser equation. So I call that the first order Colodro-Moser equation. And that's how the zeros move when you put the y to the n choose 2 and write y is e to the minus gamma and think of gamma as time. The roots move according to this trigonometric first order Colodro-Moser equation. And that has been studied a lot for real time. And it hasn't been studied much for complex time, which is what we care about. We care about y in the unit disk, so we care about complex time gamma in the right half plane. And again, I have numerical experiments about Colodro-Moser at complex time. And I think that some of these properties will hold when the roots are not too unevenly spaced. And exactly what that means, I don't know, but something like that. So that, I mean, just the question of the behavior of these roots for polynomials is an interesting question related to Colodro-Moser. But anyway, the class where these positivity properties holds seems to include at least the deformed exponential. Okay, and these properties that I mentioned before apply to formal power series, not just entire functions. But then the fourth thing, you want to be working on entire functions, and you want to know, are the leading root or the other roots analytic in the unit disk? That is to say, is there no collision of the roots? And so, as I say, I believe it holds for the deformed exponential function, and for some subclass of Laguerre-Polya class. So that's the point here, that you put polynomials with negative real roots, and if the negative real roots are not too unevenly spaced, then I believe that they will avoid colliding. The point is, or another way of saying it is, if you make a situation where you have maybe 4 roots, one here, and a pair near each other, you can concoct it in such a way that these two will collide at some complex time in the right half plane. So you do need the roots to be not too unevenly spaced. And so there's, I believe, some subclass of LP plus where this property should hold. And so this is the question, can any of this be proven? You can see some of it is questions in complex analysis. I mean, like Alex's theorem about the roots not going off to infinity in the unit disk. And that theorem probably generalizes beyond the 1 over n factorial. Probably in place of 1 over n factorial, you can put anything that's not too rapidly varying, right? Because he was relating it to a theta function where what you have is like ones, but also ones running down to minus infinity. So he had to deal with the fact that for n less than 0, the coefficients are 0 rather than 1, and for n positive, the coefficients are 1 over n factorial rather than 1. You could probably, make that more general. So there are various analytic things. And then there are these positivity questions, which are really questions about formal power series. And I have no idea whether they should be proven by analytic methods or combinatorial methods or algebraic methods. I mean, I really have no idea. So I hope, I hope I've gotten somebody interested. There's something interesting going on here. And well, I think there's a lot of different things interesting going on here. And if any of it could be proven, it would be very exciting. So as I said, in 2011, I gave 4 lectures on different aspects of this, so you can see more details there. But basically, nothing has been proven, or nothing significant has been proven about this since then, as far as I know. So thank you, and I really hope somebody will have a good idea for proving these conjectures.